about 3D printing, but we're talking about two key issues. First is rapid. Second is printing in solid state. I'm from Nanyang Technological University, Singapore. So what is the application background of that? We're talking about additive manufacturing and the potential applications. There are two types of directions. First is microgravity. The second is strong random vibration. What does it mean? Okay, this is the station, space station. If we want to print anything over there, how are we going to do that? But do you know that it is possible using FDM? But as you can see, this is slow. It's pretty slow, just like all FDM. And also, there's a potential problem because the particles may fly away and no gravity. So it's another issue how we actually print it. It's also a challenge. This idea actually proposed some years ago, 6 or 7 years ago, by NASA. They have firstly printed in space. Again, FDM. So it's slow and with problem because the gravity issue. So let's go back to our Earth. If we want to print something over here, the boat. Okay, so the storm, so we have a severe vibration, strong random vibrations kind of situation. How are we going to print something over there? If we want to print properly, current technologies all have the limitation to print in this kind of environment. And where it's possible, is another scenario. Where it's possible, we print something during maneuvering, for example, in this tank, where it's possible. So the logistic tends to be easier, or everything can be actually printed during maneuvering. And when you need it, you don't need to stop, or you don't need to print elsewhere and then transport to here, because everything can be on spot printed on demand. All we need to prepare, they are just a solid piece of material so that we can print it. Now, whether it's possible, the first question, as I mentioned, is that first requirement, as I mentioned, is rapid additive manufacturing. Current technology, a pair of shoes, Adidas, they can actually print it using DLP to rapidly print the sole. This is much, much faster than FDM. This is a continuous liquid interface production. Another possibility is that instead of using this kind of DLP technology, another possibility is volumetric additive manufacturing, in which we have two laser beams to cross link a particular point. And these two beams join together. So this is an example. It's rapid because, for example, this kind of model can be printed within minutes. Right, so this is rapid, both of them. But however, they are liquid. They use liquid as raw material to print. And therefore, if under strong vibration, this is also a problem. So anything we can produce in a solid state, of course, for example, this crystal, we can actually process it in a solid state. Let's see how we actually do this. I believe most of you knows what it is about. And this basically using laser and point into the crystal and cause micro cracks. In the end, the result is this. Of course, this is kind of micro crack inside of the solid piece. But this is not printing. Can we use same kind of concept, but in another way, to achieve solid state rapid printing? Here's an example. Let's suppose we have a material. We can somehow melt it. Okay, but
sorry for interrupting, Dr. Wei, but
yes.
Can you please change your slides? We cannot see what you're talking about.
You can't see my slide?
Yes, now you have changed it.
I just changed it, or I changed it from beginning?
Not from beginning, just now.
Can you see this screen now?
Yes, now we see.
But if I change to this, you can't see it?
No, we don't see any changes now.
Wow. Can you see the videos before? It just happened for this slide?
Yes, it's just working there.
Wow. Okay, let me try to see whether I can manage to go through. Now you can see this slide, right?
Right.
Okay, so let me discuss one by one, slide by slide in this way, rather than using the alt show motion. Okay, from here, let's say we have a piece of material which is solid, and we turn that into another phase, but it's still solid, which means that it won't be able to flow. And we put a mask on top of it. And then using laser to cross-link through this mask. In the next step, we can turn that by 90 degree, turn it by 90 degree because it's solid. It doesn't matter if we swing it by 90 degree. And then we use the same kind of mask and then cross-link again using UV light. And the result of that, something like this after removal of the mask. And then what we can do is that we can remove the rest, which is uncrosslink part, and the remaining is crosslink. This is what we want. So this is the whole process from beginning to the end. They're all solid. Okay. Only the last step we actually remove the uncrosslink part. So the remaining is crosslink. Another possibility is, sorry, this now is a bit small because I can't use another mode to show this. We also can use two beams, laser beams, just like volumetric additive manufacturing. Unfortunately, there's another, let me see whether, okay, let me increase the size of it. Sorry, it's a bit messy. We can use two beams, cross-link it. One is a flat beam, another is a point line beam. So after this, what you get is, after removal of the uncrosslink part, the result is a spring. Okay, so this is the case that we can use volumetric additive manufacturing, this method, to print something rapidly. The top part, this part, just illustrated only. Schematic is illustrated here only. That is dual crosslink, use dual masks. Okay, now you may be wondering how you actually can achieve that. Is anything you can demonstrate this concept? Here we go. We utilize a special type of thermal gel. This thermal gel has the feature that at room temperature or body temperature, about 30 degree, that is solid. But if you cool it to about slightly above 10 degree, it starts to melt. If you cool it to 4 degree, it becomes liquid. So this is a kind of special thermal gel which melts upon cooling instead of upon heating, as we understand based on physics. Okay, we utilize this material, but we need to make sure that this material, this hydrogel, is able to be cross-linked using UV. So here we have a video to demonstrate this concept. I hope that you can see this, although this size is relatively larger. So it's a solid. You can refer to this one. It's strong enough. We can place a few coins on top of it without sinking. Now we can turn that by 90 degree after first cross-linking. Use the same mask, and we use UV to shine on that for 1 minute. And the result of that is solid. We need to cool it in ice water and then take it out. So here we go. We successfully produce by dual cross-linking this cross shape in solid state. But only in the last step, we actually get rid of the uncrosslink part. The tricky part actually is that we needed the shared memory effect to ensure that the model we printed is precise, because without it, during remove the uncross-link part, the crossing part may be distorted. So we need to check the shared memory effect, as shown over here. The shared memory effect. Okay, this is the original shape, and we can cool it and compress it. So this is after programming back to room temperature. It can maintain this shape. But if we cool it again, it will fully recover its original shape. So we successfully demonstrate this is a kind of rapid additive manufacturing method, and we can cross-link in the solid state, and it has very good shared memory effect, so it's able to recover its designed shape. Okay, you may be wondering, that is hydrogel, which is pretty soft, although it's strong enough to put a few coins on top of it, even without cross-linking. But can we achieve the same? Use hard polymers, for example, polyurethane, PLA, those type of material commonly used in 3D printing. Yes, it is possible, but we need to find a special type of polymer. We know that between thermoset and thermoplastic, there is another special type of polymer that is called Richmond. The Richmond is unique in the sense that it has the reversible cross-linking, in which at room temperature, it is thermoset. But if you heat up to very high temperature, the cross-link disappears, and therefore it becomes thermoplastic. So this is the unique feature of Richmond, in which we have there is a reversible cross-linking over there. So you can refer to this paper if you're interested to know more about Richmond. Okay, now let's take a look at the internal structure. This is an illustration of the reversible cross-link, and this is a percentage of cross-linking, and this is temperature. If we heat up at this temperature, this actually is a temperature above its melting temperature, well above its melting temperature. Later I'm going to explain in an example what is the melting temperature, what is actually the temperature is the material start to melt, start to flow. So if you heat up this temperature, cross-link start to gradually disappear until upon heating to over here. There isn't any over here. There isn't any cross-linking anymore. Upon gradual cooling, the cross-linking reappear, and up to this point, it's fully reversed back to the original cross-linking state. So we have an internal reversible cross-linking system inside of Richmond, and when the material melts, it is still cross-linked, and because the cross-linking, for that we need to heat up to much higher temperature, for example 30 degrees above its melting temperature. You may be wondering, well, is any such a material there? Yes. A particular Richmond we used, you can refer to the previous slides, the paper in the previous slides, that is about a commercially available Richmond. But of course, we needed to modify it. We need to modify it, make sure it's going to be cross-linked again permanently. That is something we are doing. Now let's take a look at the Richmond, the commercial Richmond. The unique feature of this commercial Richmond, as a Richmond, is that DSA result, which reviews this is melting, and this is crystallization. So there are two kind of events during heating, melting, during cooling, crystallization. As we can see, the melting temperature for this particular Richmond, which is a TPU, thermoplastic polyurethane, that is about over here. So that if you heat up to about 75 degrees, it's supposed to be fully melt. Okay, but however, if we refer to DMA testing results, this is temperature, this is strain, because we use this kind of cyclical loading with a very tiny force applied on it. So that you can find that if we heat up to over here, 45 degrees, the material is pretty elastic. Even we heat up to over here, 90 degrees, this material is still elastic. It doesn't flow, okay? Because of gravity, there isn't any such a flow event because of gravity. So the material actually is pretty strong. And if you refer back to DSC result over here, 90 degrees is well above, 90 degrees somewhere here, which is well above its melting temperature. Well above its melting temperature. The material is melted, but still in solid state, just like semi-crystalline polymers. And then, if we heat up to over here, well, which is about, over here, about 100 degrees, you can see the material is still elastic, although it's not elastic, its elasticity is not as good as shown over here and here. Which means that at 100 degrees, which is somewhere here, the material is still able to maintain the shape. Only when we heat up to over here, which is close to 110 degrees, the material starts to gradually deform. That is because of the material is able to flow. So until we heat up over here, the material is able to flow. But before that, the temperature below 100 degrees, the material is able to maintain its shape, just like a semi-crystalline material. But the difference is that the cross-linking is it's reversible, which means that if you heat up to even high temperature, eventually the cross-linking is going to fully remove. Okay, so this is a unique feature of Richmond. Now, to enable Richmond to be 3D printed using UV, we need additional requirements. The first is transparent. Over here, it shows that the material is transparent, but only if you heat up. This part has been heated up to above its melting temperature, but this part is without heating to its melting temperature, so the material is still opaque. But this part, if you heat up to above its melting temperature, the material is transparent, so that the laser beam can pass through it. Okay, this is very good for cross-linking using UV. The second thing is that with shear memory effect after cross-linking, as shown over here, this is the original shape. If you heat up and stretch it, yes, it's maintained this shape, but if you heat up again, it's fully recovered its original shape. So it has very good shear memory effect, and therefore we can make sure that the material is able to maintain the shape after remove the uncross-link part. And how hard the material is? I said this is TPU. It's a type of TPU, but not the kind of elastic TPU. So that this one here shows the tensile strength or tensile stress relationship. You can see the Young's modulus is about 1 gigapascal. In fact, there are various kinds of Richmonds developed in these days. The concept of the term of Richmond was proposed actually about 9 years ago only, so it's a pretty young term. And although commercially in the market we can actually find some Richmond, but unfortunately they don't call that Richmond. Mostly they still call it TPU, thermoplastic. For example, thermoplastic polyurethane TPU we use over here. So the next step actually is that we need to make sure it's able to cross-link. Over here, we actually cross-linking using conventional those kind of cross-linker, but it's not printed out. The next step that we are doing is we need to integrate this function into the Richmond so that itself has a reversible cross-linking, and after UV cross-linking, a permanent cross-link network can be formed inside of the tube. So this is what we are working on. Now, a summary. Let me see whether you can see this. Okay, basically two types of applications: microgravity and random vibration. And because it's a solid state, it's always in the solid state. We can safely using beam. Even the environment is not so friendly, we still can successfully print it in a rapid manner. And we have demonstrated that using thermal gel, and we are now working on to achieve that using hard polymers. And the particular material I think it is useful for this particular type of application is Richmond, but we need to modify the existing Richmond to enable it for cross-linking. One is reversible itself, the intrinsic feature of Richmond, and the other is a permanent cross-link. Okay, thank you very much for listening to my presentation. Thank you.
we have completed Dr. Wei Min Huang presentation. So thank you so much, sir. So thank you for the energetic presentation for today.
Thank you.
Yeah. So so you can close the window now. Yeah. Okay. Sir, anyone having any doubts, question? If anyone having any doubt question, they can feel free to ask Dr. Wei Min.